scroll out a little bit, see if we can even arrange things just a smidge. Okay. Just a couple of reminders and things that we're looking at. The test is going to be October the 16th. So please let me know if I need to make arrangements at the testing center for sports, whatever. Please let me know ahead of time so that I can get that over to the testing centers. Because I know as we get right towards fall break, there are things like judging contests, things like PLC on both sides, Tonkawa and Enid. So please let me know so that I can get the appropriate forms and the appropriate things set up. Other thing is there is the Midwest Regional Meeting of the American Chemical Society is in Wichita. And if anybody wants information on that one, please let me know. Because that is something that is worthwhile to look at. And it's running Wednesday night, Thursday, Friday, and then there's a teacher session on Saturday. October the 22nd, I will get you more information on it, but we are going to participate in a national broadcast of the American Chemical Society National Chemistry Week presentation on that Tuesday evening. I think we start at it's either 5:45 or 6:45. I will try to get us a room over here for those who want to sit in and participate on it. And it's on Marvelous Metals is the theme for National Chemistry Week. And they're going to be talking about metals properties. For those of you who've taken Gen Chem 1 and Gen Chem 2, metals are the interesting ones because we don't usually talk about those in general chemistry because metallic bonds are different. And so it's these webinars are usually really, really good. And they do audience participation and a few other fun things. So I will send out information so that everybody we definitely are doing it over in Tonkawa. I'm going to have it moved over here as well so that people can participate. So just giving you a heads up on that one. And next week, Nano Day, Metric Day, and Mole Day is October the 23rd. Nano Day is October the 9th. And if anybody's into squid and octopi, I think next week is the International Celia, whatever they are, day. And of course, International Okapi Day is in this month as well. So, just little tidbits. Trying to get us started. So, where we were on Wednesday is we were looking at energy, and we had talked about a variety of things. So, I'm going to start with our slide. And we're going to have our little person up here at the top of the slide, and our person is going to have a mass of 50 kilograms. Now, hopefully all of you have figured out that drawing your picture is critical. Okay, that's a little better. It's still fuzzy, but that's a little better. Drawing your picture and getting your picture correct is essential. So if I do work to get me up, and at the top, I now have total energy, and my total energy is going to be my potential energy plus my kinetic energy. Halfway down the slide, total energy is still potential energy plus kinetic energy. And all the way at the bottom, total energy is going to equal potential energy plus kinetic energy. If I make my slide a tall slide, and we're going to say that this is 2 meters, we can calculate the work done to get the person to the top of the slide. I got to do my force times my distance. Now, in general, there's a cosine sitting out here, but if I'm in line with the work being done, that cosine goes to 1, and I don't have to worry about the angle. So now I'm just going to deal with my force, which is mass times gravity, times my distance. And if I have a 50 kilogram person up there, gravity is 9.8 meters per second squared, and my distance is 2 meters, I'm going to get units of kilograms, meters squared, seconds squared, which is a Newton meter, which is a joule. And we talked about how later on we're going to see that Newton meters may not be combined, and that Newton meters may stay as Newton meters. And that's related to the difference in the mathematics between what we call a dot product and a cross product. This is a dot product that gets me a scalar. If I plug that into my calculator, I'm going to get 980 joules. So if I'm asking the question, what is the total energy at the top? 980 joules. What's the total energy halfway down the slide? 980 joules. What's the total energy at the bottom of the slide? 980 joules, which is equal to the work that I put into the system. We started talking about that work is going to be related to conservative energy, or my change in energy that are conservative, and my change in energy which is non-conservative, where this is going to be heat, light, sound, those things that I'm going to lose because I can't keep it trapped into the system, which becomes important when we get to thermodynamics. Whether you get that thermodynamics in chemistry, or you get it in physics, or you get it someplace else, where I'm dealing with that energy becomes really important. But in this system, we've got conservative. So at the top, when I'm at the top and I'm at 2 meters, I have no velocity, so my kinetic energy goes to 0, because remember, potential energy, we're going to use mgh, and kinetic energy we use is 1/2 mv squared. Now at the bottom of my slide, h is equal to 0, so my potential energy is equal to 0, and I'm left with my kinetic energy. So I can find the velocity at the bottom of the slide. Alright? So if I do my 1/2 mv squared is equal to my 980 joules, this is going to give me v squared is equal to, okay, I'm going to get 2 times 980 divided by 40, or not 40, it's 50, because I used 50 this time. 50, and my v squared equals 39.2 meters squared, seconds squared. Take the square root, and I get my velocity is 6.3 meters per second.
So you put that all under the square root?
Yeah, I take the square root is 39.2. Now let's look at this for a second, because our kinematics said I've got v squared final is equal to v initial squared plus 2a change in height, right? That's my kinematics. My kinematics said that v final squared is going to be 2g, my height, and so my v final is going to be the square root of 2gh. Here I have 1/2 mv squared is equal to mgh. By conservation of energy, this is kinetic energy at the bottom. This is potential energy at the top. M's will cancel. V squared is equal to the square root of, or V squared, we'll stay at V squared. V squared is equal to 2GH. V is equal to the square root of 2GH. This comes from kinematics. This comes from conservation of energy. So I can get there a couple of different ways. Question. Okie dokie. You guys will go hit K over there and talk well? Alright. And just a reminder, over here in Enid at 1:30, I'll be in the physics lab to work problems. Alright, so we've got through that. So we're going to walk through, let's go ahead. Let's do this one. We're going to take a grocery cart. So I got a grocery cart, and we're going to give it a push. And it's going to roll down the aisle. And it's going to have a velocity when we start it of 5 meters per second. It's going to roll down the aisle 20 meters. And we want to find what is the acceleration of the cart. I want to find what is the acceleration of the cart. Initially, it may look like we don't have all the information that we need, but it turns out we do. This is going to use the work net is going to equal the change in kinetic energy, which is equal to my force times my distance. And if we remember that force is mass times acceleration, I end up with my change in kinetic energy is equal to my mass times my acceleration times the distance. So in this case, my change in kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared is going to equal mass times my acceleration times my distance. I don't need to know the mass of the cart. I don't need to know the mass of the cart. And this, let me go through this real quick. I'm going to multiply both sides by 2. I got v final squared minus v initial squared is equal to 2ad. Hopefully that equation looks very familiar to you by now. V final, in this case, as we said, it comes to rest. V initial we have. We know 2 is just a number. D is my constant. So I'm going to get a negative v naught squared divided by 2d is going to equal my acceleration. This negative tells me I have a deceleration, which is exactly what I want to have. It's a deceleration. And so if I put in my numbers, I'm going to have 5 squared, and that's meters squared, seconds squared, divided by, I still have a negative, 2 times my distance, which was 20 meters. 1 meters cancel out. I end up with meters per second squared, which tells me I've done everything right. And That becomes 25 divided by 40, and it ends up being a minus 0.625 meters per second squared. We good? All right. So now we've got a person pushes a car from rest to a speed V, doing 5,000 joules of work. The car moves 25 meters in the process. And we'll give ourselves the mass of the car. We may or may not need it, but we'll give ourselves the mass of the car. It's 2.5 times 10 to the third kilograms. We're going to neglect friction. We're going to say that this was an icy surface so that we're not going to have to overcome friction. We want to find the velocity and we want to find the force. And we want to find the velocity, and we want to find the force. Well, force is easy, because work is equal to the force times the distance. So work divided by the distance is going to equal the force. And that is going to be my 5,000 divided by 25. I don't know if I plug that into the calculator. That gives me 200 newtons. I can use my change in kinetic energy, which is going to be 1/2 mv final squared minus 1/2 mv initial squared is equal to my 5,000 joules. Our initial velocity was 0. The final is going to be 1/2 m. It's going to be 5,000. So V final squared is going to be 2 times 5,000 divided by the mass, which is 2.5 times 10 to the third. This gives me 4, and this is in meters squared seconds squared. So the velocity final is just going to be 2. Alright, we're going to complicate things. Can't stay that easy, right? Never can. Alright, what we're going to do is we're going to take a situation. And most of us have seen this thing happen before. I've got something that's called a pile driver. And the pile drivers are used to drive beams or items into the ground. Okay? And how we do it is we drop this heavy weight from a distance and we let it hit the ground. So we're going to walk through this problem and look at some of the physics that's going on. Does anybody watch The Mysteries of Oak Island? I have. Anybody watch Mysteries of Oak Island? Okay, because they went through and they put in a whole bunch of panels to block the bay so that they could keep the water out of the bay. That's where you've seen it before, but any place that's doing construction where they've done a basement and they start pounding in I-beams, this is the kind of thing that they do. So we're going to start out that the height that we're going to drop our pile driver from is 5 meters. And the mass of this thing is 2,000 kilograms. And when it hits the beam, okay, when it hits the beam is going to go 12 centimeters into the ground. Now what we're going to do is we're going to look at this from various parts of the problem. And that's what happens with a lot of our physics problems that you need to look at. You need to kind of break it apart. You can't necessarily do it all at once. So the first thing that we want to look at is what's the potential energy that we're putting into the system. Well, that's going to be pretty easy because that's going to be my mass times gravity times the height. And I'm going to put my 2,000 kilograms. We've got gravity, 9.8 meters per second squared, and we're going to drop it 5 meters. And so I've put 98,000 joules of energy into my system. Now, one of the key things about this is we're also going to have to figure out our coordinate system. We're saying that that right there is 0. The top of our I-beam before it goes into the ground, we're saying is 0. That's going to become important when we start looking at what's happening to the beam after the pile hits the beam. So we're going to get conversion of energy, right? We're going to get conversion of energy. So if I have this potential energy right there, we know when the pile hits the beam, all that potential energy is now equal to kinetic energy of the pile. Because what we're going to need is we want to look at the kinetic energy of the pile. And so I'm going to want to know the velocity of the pile when it hits the ground. So it's 1/2 mv squared is equal to 98,000 joules. So v squared is going to equal 2 times my 98,000 divided by the mass, which was 2,000 kilograms. I can find the velocity, and that velocity ends up being 9.9 meters per second. Now, we're going to assume that we are not losing any of our energy when it hits the pile, for the sake of this problem. But we know that's not correct. Because when the pile hits the I-beam, what happens? Picture in your mind. I'm going to get sound. We're going to hear a big bing, right? We're going to hear a big bing. We're also, and if I'm standing close, what else is going to happen?
Vibration.
I'm going to get a vibration. Okay? This is why Mother Nature's not fair. Okay? Mother Nature's not fair because I put energy in, I did work to lift up my pile, and then I let my pile fall, and Mother Nature's going to take her cut. Mother Nature's going to take her cut because we're going to get sound. We might even get sparks. right? We might even get sparks. And we know we're gonna get vibrations, so it's really not fair because all that work I put in doesn't actually go into putting in the beam into the ground. That's the second law of thermodynamics, and we can't break even, right? We can't break even. But for the purposes of this problem, we're gonna say we can break even, and we're gonna go ahead and do the calculation because what we wanna know is we can do this, and we're going to look at the change in kinetic energy that results in my I-beam. Okay, the change in kinetic energy that results in my I-beam. And if I do that, I'm going to get the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared, and my final velocity is 0. I end up with my change in kinetic energy goes back to my 98,000 joules.
Yeah, so no math at all.
That doesn't take any math at all, exactly. Now, if I want to complicate this thing and look at the whole system, I want to know, because I'm picking out the material that I have to use for my pile here, okay? And we all know certain things. I know if I take a hammer and I use that hammer to hit a nail, the nail goes into the wood and life is good, right? But if I use that same hammer to hit an ice cube, what happens? It shatters. And those are related to the material properties of my material. So as an engineer or as somebody who's doing something, I've got to know what force is being applied to my pile. Now, if you're on the medical side of things, okay, if you're on the medical side of things, and I'm having to do a hip replacement, I want to know the force that's going to be applied as I put my leg to the ground against that lovely new titanium piece that somebody's put in somebody's hip. And I've got to deal with what the force is going to be on the bone and the titanium hip to make sure that I am not shattering a person's bone every time they walk. Okay, so if I'm looking at it from a medical physics perspective, I need to know this force. So this is going to complicate our problem a little bit, because we're going to have to look at the system. So we've looked at the system so far as the pile hitting the driver, or the pile driver hitting the what they call the pile, or the I-beam. We've looked at the I-beam as it gets into the system. But what we haven't looked at, the whole system together, and this is where we use the entire work energy theorem. And the work energy theorem says work is going to equal my change in kinetic energy plus my change in potential energy. And in this case, my work, okay, because work is going to be in the opposite direction, I have to do this. So I got 1/2 mv final squared minus v initial squared plus mg, and this is going to be h final minus h initial. Now this is where it gets tricky when we look at the entire system. Okay, we're looking at the entire system. We want to find this force on the pile so that we know we pick out the right material. We're using our entire system to do it. Well, my initial velocity of the system, my initial velocity of the pile is what? At the very top, what's my initial velocity?
No.
When I start, what's my initial velocity?
0.
0.
Sorry, I was like, what?
Okay? When it goes at the end, and I'm at the very end and the pile is in the ground, what's my velocity of the system? 0. I don't have no kinetic energy that I've dealt with. Now, here's the other tricky part. Since we're dealing at the point where the force of the pile onto the pile driver, this distance, okay, that distance is 0.12 meters. It's that 12 centimeters that's going into the ground. On this side, I've got the mass of the pile driver, times gravity. My final height, okay, my final height is below grade. So I've got to do a minus 0.12 because I changed my 12 centimeters into meters. And my initial height was my 5 meters. Well, I know my pile is 2,000 kilograms. Gravity is 9.8. The entire distance traveled going downward is a minus 5.12 meters. My force, which is the force of the pile onto the pile driver, is actually positive because I've got, this is gravity going down is negative, my force is in the opposite direction is positive. So I'm going to take my negative 0.12 meters negatives cancel, yay, you like that. And this works out to be 8.4 times 10 to the 5th, and this is kilograms, meters per second squared. These meters cancel out, I end up in kilograms, meters per second squared. That's a Newton, so I'm in Newtons, life is good. And that's the force that the pile is going to experience when it hits the I-beam. So depending on your problems that you get, you may have to break them apart. So we're about to do one that we got to break apart. Another one that we got to break apart. Guys good over there? Questions? Okay. Alright, so we've done ski jumpers. We've done slides. We're going to do more slides. Okay? Oh, the slide that we have done so far, we have the slide go all the way to the bottom, right? Go all the way back to the ground. So this time we're going to do it a little differently because we want to do that because that's not fun, right? So I've got a slide, and we're going to go height h up, and this is a height little h. What's the difference? My slide doesn't go all the way down the ground. And we've all done this, right? If we've gone down the slide into the pool, right? We're above the edge of the pool, and what do we do when we fly off the end of the slide? We land a distance away, right? We don't land right at the bottom of the slide. The object is, we're actually, when we come off the slide, we're going to go something like that. Right? Okay? And we're going to use a frictionless slide. what we want to do is we want to find D, the distance away from the bottom of the slide that we get, based upon these two heights. Okay? Based upon those two heights. So what we have here is this part of the problem going from the top of the slide to the bottom of the slide is an energy problem. This part of the problem is a projectile motion problem. Okay? So, what do we know right now is that the total energy in the system, my potential energy at the top has got to equal my energy at the bottom. Or my total energy here has got to equal my total energy there. So, let's do that. So, total energy at the top is just going to be mgh. Total energy at the bottom of the slide is going to be mg little h, because I'm not all the way down at the bottom, plus 1/2 mv squared. So I'm going to put this together so I get mg capital H is equal to mg little h is equal to 1/2 mv squared. Now we know that I'm probably going to need velocity because this is a projectile motion problem. Okay? We know that that's a projectile motion problem, so I'm probably going to need velocity. So I'm going to solve for velocity. So I get mg big H minus mg little h is equal to 1/2 mv squared. My m's go away because I can divide them out. I'm going to factor out gravity. So gravity, h minus little h, is equal to 1/2 velocity squared. My velocity squared is now equal to 2g h minus h. Now, I'm not going to go ahead and take the square root because I may just leave v squared in its term, and so I'm not going to take that step just yet. In my projectile motion part, my y is independent of my x. Okay, my y is independent of my x. So we remember, hopefully, okay, so we're going to put this one this way. We remember that my change in y is going to equal minus 1/2 gt squared. Because my distance, I've got to worry about, for my distance, I have to have the final velocity times time. This is my x side, this is my y side. Since I have no acceleration, I've got to have time, so I'm going to need my time. Now my change in y is going to be minus my little h. And I solve for t, so I end up getting, those will cancel, so I get 2h divided by g is equal to t squared. So t is equal to the square root of 2hg. So what I'm going to do is I'm going to plug that into there. So my distance is now equal to my velocity times the square root of 2hg. Well, that's messy to work with. So what I'm going to do is I'm going to square everything right now because it's messy to work with. So I'm going to get d squared is equal to v squared 2hg. Well, that's nice. Because we know what v squared is. So let me clean it up a little bit. I'm going to put d squared g divided by 2h is equal to v squared, but we already figured out v squared, and that was 2g h minus h. I'm going to get you back here where we got that. So I'm going to clean it up just a smidge. I get rid of gravity because I no longer need it. It's on both sides of the equation. It's on both sides of the equation. So I'm going to get that d squared is equal to 2 times 2 is 4, h minus little h. So depending on where you want to stop or specifically what the question is asking you, if I want to know the distance based on those ratios of heights, it's going to be the square root of 4h minus h. And I can continue to clean it up a little bit because I can take the 4 out of the square root. And I'm going to get 2 times the square root of h minus h. It just depends on where you want to end up at that point and what the specific question that WebAssign may be asking. But that does tell you, depending on how high above my surface, where I'm going to land. Questions? Guys good? Okay, let's do some
Sometimes my homework makes so much more sense. Yeah.
Alright, so let's take a spring. Okay, and we're going to stretch my spring 5 centimeters. And what we want to know is and we know what's going to happen when we stretch the spring. We're going to let it go, and it's going to do what? It's going to go back this way, right? And if I don't have any friction and I don't lose any energy, it's going to compress the spring, and then it'll come back and go that way. And so this is 0. We're going to stretch the spring 5 centimeters, and we want to know the velocity when it passes 0. We want to know the velocity when it passes 0. And we're going to start with this spring, its properties, because we said that K is related to the spring. And we're going to use that this K happens to be 163 Newton meters is my spring constant. Just pulling a number out of the hat. And so we've got that. And we saw Wednesday that the potential energy of the spring was equal to 1/2 kx squared. Okay. I just happened to be a sloppy today, and that has a number 2 underneath there. Because I've had lots of people ask why I write Z's like this and I write 7's like that. It's an international convention to write Z's. It's called a Latin Z or a Latin 7. and depending on where you are in the world, will depend on how you write your Z's or Z's and your 7s. And one of the reasons is because people have sloppy handwriting or can have sloppy handwriting, and I can't tell whether that's a Z or a 2, but in my handwriting you'll be able to tell because I'm writing a Z that way. Same thing with 7s, because I know a lot of you have numbers that look like that, and that's actually a 7, because I've graded enough chemistry lab papers to know that people have handwriting that looks like that. So in order for me to know that that's a 7, doing that is helpful. And it happened to be because when I was in high school I was in Panama, so that's why I write with a Latin 7. Okay? And my first typewriter that I learned to type on had an Enye in it. So, which is very helpful. So a keyboard with an Enye is kind of different than a keyboard with our standard N's. So it's just a little different. Huh? What'd you say?
It's on the side.
Somebody knows exactly where it is. And then on the Spanish keyboard, there's another one for the double L too, isn't there? There's one that you can put the double L in, and then there's another one in there somewhere. And actually the keyboard that I did also had this lovely letter. Oh God, can I write it right? Maybe I have to go the other way. It's an A, and we get the E. It's that letter right there. Usually you'll see it in words like encyclopedia. Most places we see it now, we don't typically see it all the time, is that you'll see it in the pronunciations. It's how you pronounce the different letters. And depending on your keyboards, you may or may not have that particular letter. It is a weird AE, and it's a combined AE sound, and the most common word that people will see it in is encyclopedia. So, fun little asides, and it's partially because I actually had a student ask me yesterday about why do you put the line through the Z? And it's related to where you are and how, and actually I've kept it because it makes numbers very easy to tell. So my potential energy is 1/2 kx squared. So if I want to know the potential energy that I put into my system, well, that's pretty easy. I'm going to put in my 163 divided by 2, and I'm going to do my 0.05 meters, because I converted my centimeters to meters squared, and that gives me 0.204 joules. Now, I can use conservation of kinetic energy, the total energy in the system. When it goes through 0, my total energy is just equal to my kinetic energy. And let's go ahead and say that my block is 50 grams. So if I go ahead and put it in kilograms, my block has a mass of 0.05 kilograms. And 1/2 mv squared is going to equal to 1/2 kx squared. Halves cancel. I end up with v squared is equal to k over mx squared. I can plug in my numbers, my 163 divided by my 0.05, and then I've got my 0.05 meters squared. This gives me v squared is 1.8 meters squared second squared. V ends up being 2.85 meters per second. Has anybody started the homework?
Yes.
Did you get any curves in your homework?
I've only gotten 5 questions, so I haven't gotten any yet.
Okay, because I don't think we've talked about it yet, and I've got different physics books, and I've got some notes here, and I think it's in my engineering physics book, but I am going to give you a definition, just in case. Because I know we've talked about it in terms of describing why we get an acceleration if I'm traveling around a circle. So if I'm traveling around a circle at a constant velocity, or constant speed, because I'm not at a constant velocity. I'm traveling around the circle at a constant speed, so I'm traveling around at 5 meters per second, and I haven't done anything other than if I'm here. So if I look at my velocity at this point, it's going in that direction. If I look at the velocity at this point, it's going in that direction. If I look at the velocity at this point, it's going in that direction. So I get an acceleration just because I'm changing direction. Okay? I get an acceleration just because I'm changing direction. And if I look at this, that acceleration, I can draw the pictures, and I know when I get to rotational motion, I actually show videos associated with it. But I get this change in here that's related to R. And we call this centripetal acceleration. And that's a velocity squared divided by my radius, R, as I'm going around a curve. Okay? As I'm going around a curve, my acceleration towards the center is going to be v squared over r. And if I look at my units, this is meters squared, seconds squared, divided by meters. Meters will cancel, and I end up in meters per second squared. This also can be derived using F is equal to ma, which is equal to g m1 m2 over r squared. And using Kepler's law, we can come back and get that centripetal acceleration. And the reason I want to make sure that we have that is because there may be some problems where you need to have and do some evaluation on your potential energy associated with a curve. And my centripetal acceleration is v squared over r. And problems where you might see it might be something like this. I've got a ball. It comes down here. You're given r. And I might have to calculate work associated with that particular thing. And if my work for going around a curve, or my force, is mass times my acceleration, and mass is times my centripetal acceleration, then that's going to be mass v squared over r. And if this is a height h, we know what the velocity is down here, right? Because I get mgh is equal to 1/2 mv squared. I can look at the forces that come into play. And it becomes particularly evident. Have I shown in here the human person doing the loop-to-loop? Okay, nobody? All right, so how many played with Hot Wheels? You played with Hot Wheels? I played with Hot Wheels a lot. You got the loop, right? You got the loop. Okay? My loop has a radius r. And in order to make this work on the loop, my force due to gravity and my force at the top of the loop have to be equal. Which means that my mg has got to kind of balance out mv squared over r. So I have to have v squared over r is equal to mg to get there. And let me see if I have that one with me. Because what we're going to see down the way is there's a problem that we do that needs to know how high this has to be in order for my car to make the loop-to-loop. And most of you have done this if you've ever played with Hot Wheels in the loop-to-loop. Because you have gone up, how far, where does my little car have to be in order to make the loop? And I'm not sure if that happens to be one of the homework problems that you have.
Is it towards like the top building? Like above the loop?
Yeah, well, usually you do this in H compared to R. So how far does H have to be compared, or how far, or what is H compared to R? And it relates back to, I have to have v squared over r. Let's see, do I want to do another problem? Because
I think it was in one of those flash drive ones that you took off.
I've got several. And we did talk about work, or power, right? I did give you the definition of power. And we actually did a crane problem. Now, we'll try it. I know they've been having trouble, but we'll try it. Okay. Everybody's familiar with parkour, right? Okay, this is a parkour guy. Let's see if it will go through. We'll give it a whirl. Okay, looks like it's going to work. Now the question is, do I have sound? I don't want to mute. Nope, I got sound. I got sound. Maybe we'll find out if I have sound. Nope, I don't have sound over here. So let's see if the sound is an issue here. Not that you have to have a whole lot of sound for this, but there we go, volume.
You gotta turn it up.
Well, this looks like I've got full sound.
Well, on the other, there's another picture in the middle that showed that you need to adjust it. Turn it on.
There we go. This is on the screen here. There we go. Let's see if we get that. Okay, we got sound. All right. Now we just got to put the sound level a little bit. Okay. Okay, I don't know why we're getting flickering, but we are. There we go.
My name's Dan Walters. stuntman who does tumbling, gymnastics and parkour. I'm attempting to run the loop. So I've seen people do it on a skateboard before, I've seen people do it on a BMX before, but no one's ever tried it on their feet, so it's been nice to be the first guy to actually run it. It looks a lot bigger than what I thought it was going to be. Yeah, it must have been not the easiest thing.
I'm gonna turn it up just a little bit.
To be one of the first people to do things is always one of my ambitions. You know, I want to try and keep pushing the boundaries even further and further and see how far people can go.
Basically boils down to the centripetal force. You need to keep on accelerating. So you need to reach a certain speed. And I've worked out, it's quite good news actually, the speed at the top is 8.65 miles per hour. That's it.
Okay. 3, 2, 1, go. 17.
Somebody's showing that one back. Well, this one's it. I know I've said that 3 times now, but this one is it. Well, I'm close, I reckon I'm close.
Get close.
You can't really go any further until you take the match out. Yes, get rid. Yeah, go for it.
It's almost like he has to land his left foot or his right leg before he actually stops.
Yeah, the trick actually for this isn't the speed, the trick is body mechanics.
Yeah.
It is a conservation of energy problem to make sure that it has the right amount of speed for the centripetal force to balance the forces at the top. So you can actually get it kind of weird while we're getting the flicker, but I'll have to report that one in there. So that's one of the things that when you start working the problems, you're balancing out. You're having to look at where's my kinetic energy, where's my potential energy, and where are things going to go together. I'm going to stop there because to go further is probably going to overwhelm. And it's a good place to stop. We'll work more problems on Wednesday, ready for a test. And I'll do problems at 1:30 over here. Guys good over there?